Yeah, so that's also something I've been wondering about as well. Scenario like that, you would expect a more random orbit. So I think that is testable by looking at if we could eventually get the orbit of the companion itself. And then if we could also potentially look at the spin orbit alignment of the planet. So in case something more like Capture, where it formed on its own core fragmentation process, all of those vectors would be not very unlikely to be aligned in the way that would make sense with disk formation. So that's one method of testing it. It's not impossible that it would form through a process like that. It's just this is a relatively low density area, so the probability of capture events are not that high. And there are a few of these systems that are known. So I think the odds of forming a handful of these systems through that method is a little unlikely.
Okay. Let's give her one last. Next up, we have Sue, who's going to be talking about rotation and abundances of low mass stars, brown dwarfs, and exoplanets.
So I'm a professor at Northwestern University. Today, I'm talking about rotation and abundances of the low mass stars, brown dwarfs, exoplanets with ocean spectroscopy. And before we get started, to acknowledge there's a huge collaboration effort across different institutes. And then especially given there's a bunch of names that being in both things, they're presenting in this conference. Jason will be also giving a plan talk on Friday. And the rest of us will be giving the also posters. So first, thanks for my introduction by Austin and Emily. So I don't have to give much of a intro for how we care about this environment, this body system. But these are kind of like two substantial things I mentioned, which are benchmarks. And but I also point out we also love these closer bodies because a lot of them are also benchmarks, which means they have like diagonal masses. So we can also from the whole star. If they actually, for example, the red one, like the stair edges, so we can know this in kind of both parameters and order to find between one object, Simpson B, Simpson B, and I also have a B that we heard a lot over the past few days. And so intro, I don't actually have to introduce again, is the C-square ratio that we care about. That's basically because the Einstein can will tell us the different how the planet will form, but for the brown dwarfs or the stars or constellation companions, we expect they share similar C-square ratios. And these can also serve as a benchmarks for a lot of things that we do with the retrievals. And one of the observational evidence we found, like by comparing the literature by Kill and Hart 2023, they compile a bunch of like hot GPUs and compared to a bunch of like lower higher mass companions, but they found C-square ratios are drastically different compared to this population. So it's kind of like an observational evidence that we found that are so different so far. Also, we also care about isotope ratio. And in terms of rotation, so from we can look at this regime as it goes to higher mass stars. So in Johnson Martin and 2011, they found like for the M dwarfs that's on the 40 convective boundary, it actually spins off first, and then over time they actually kind of spin down, and there's a huge population, but there's a trend where they're spinning down and in terms of level time scale compared to higher mass FGK dwarfs. And the mechanism is similar, which is like ejecting these magnetic winds, which release some angular momentum. And also Johannes and conversely, they found kind of the spin up generally for kind of like a 1 to 80 junior mass objects. So part of the simple restriction and observational constraint, like 20 hours of rotational period, they couldn't really pin down the same trend for like between 1 to 30 junior masses. So it's kind of positive. Mara Bryan and 2020 found like spin up for these tiny mass objects between about 5 to 20 junior masses ish. They actually spin up So this kind of puzzle in between is like 20 to 30 minutes under the mass regime. And here comes with the high resolution spectroscopy. So if you have a high resolution spectra, then you can pinpoint the wave velocity pretty precisely. So that would be good for studying binaries. And also, if you go pretty precisely, you might be able to use exomoons. But here's a first talk. I will focus on these and I also. So this is basically the which you see the spectra being broadened. And if you run the cross correlation function, you also see for factor here, the cross correlation function will also broaden as well. And for abundances, these the different line species would tell us how depending on how different the line shapes are and how deep the lines are, will tell you the difference in abundances, C-to-O ratio, isotope ratio. That tells about the formation and evolution history. And Chih-Chun is kind of the instrument upgrade from the near spectrograph. So it injects the light from a single fiber through the near spec high resolution, which is like resolution of 35,000. So 10 times the near spec. And then, so we were able to follow within most of the objects whole size H magnitude of 5 and 10, and then within 4 seconds mostly. And here's just to show this is a point to HRE terminal planes. And if say the plane is on the red fiber rotation, and then light will be dispersed into these 4 different fibers, but one of them has a planet light, and the rest would be only mostly just speckle. So we're still kind of bound by spectral, but we were able to model it honestly. And just to show the performance of how we can do this Chih-Chun, so Jason Wang, actually just from last week in SPIE, and also with the archive as well, it showed Chih-Chun is able to probe into less than 90 milliseconds. And then we were probing into 10 to minus 4 millisecond and all the way down to like 10 to minus 5-ish in the 400 millisecond. And this is about in the closer regime, this is 2 times above full noise limit. And to the right, just to show how Chih-Chun is performing compared to other similar resolution and even medium resolution spectra. This is actually the best compared outperformed or at a few points from the Paris Plus. So I think it was doing and so far better than these 3 instruments. If we exclude gravity is amazing. And just show the gallery of how it has detected so far. That includes Julie's Fairberg, Rossberry BV, and then there's about almost 30. Some of them are brothers, and then private subjects. Some of them are exoplanets. But this is about 30 or so. Here, I want to shout out to the 2 objects from Ben Sapien and Clarissa. They will be presenting posters throughout this week. So feel free to ask them about these benchmark systems. And here, please don't tweet this. So recently, we detect PSMVB. So there's a contest, there's a finance coding, and then we have like C2O from the disk, so the goal is to constrain the C2O on this planet, and then we can tell us about the formation and also the rotation. So you can see CCS are still kind of low, so we're trying to like validate if we can really pull the information out. This made us pretty exciting as a team. We observed after the post upgrade back in May, and after meeting some of the instrument limitation, we start to see this detection. And here just to show how Chih-Chun modeling out this like huge spectral blocks. And here's the paper that was recently accepted. Just a beta system. One of them I showed this is a brown dwarf mass object detected by the process. It was the first extreme mass around HF star. The flag was actually the star. The observed like plus spectral flux spectrum, because there's also spectral. And we use sky flux to model the spectral contribution, and then use actually so many different models. For example, Sonora, data setup, and then we showed how we got a consistent C2O design, and then across different model assumptions and Splinter. Just to show how we can actually model from the KPIC. And we don't want to just show or learn one from under benchmark. So as a population, Jerry's one recently led a paper about 8 young companions. And then these mostly have like we have a whole set information. Some of them we measure ourselves, and then the goal is to we found these are basically consistent with the whole star in terms of C2O, and we show pretty a similar slope methodicity, so C2O ratios as well. Another exciting result from this is it has doubled the current C carbon isotope ratios on 12 CO to 13 CO, and then our result is actually consistent with the local ISM carbon isotope ratio. And another result from the so now it's fermentation, and so if we go to a like lower mass regime there, Beijing 2018, we're thinking if the mass is like toward the planetary mass, and because of the interaction with the base, let's stimulate dependence, and then to the mass to the square, and actually we should see a speed up toward a lower mass. But actually, so it's being mentioned by Jason and I was from 2021. We kind of after having almost 30 objects and we didn't find any clear correlation in terms of either including isolated objects that's to the left or just companions. So those all seem to have much larger scatter. So last but not least, and recently, so I like to publish another paper from the Apogee survey, and basically we're looking at different clusters with the VSI, with the cluster ages, and as well as the rotational period. But the idea here is to see this actually spinning down toward this mass spin, and this is between 50 masses to 0.1 masses. So we'll see our mass spin is kind of still spinning down before the object is sensitive to just between 0 to 80 masses, which are missing benchmarks, including some of the individual isolated object rotational period in the clusters. We see those increase in VSI, which means they're actually spinning out for this mass spin. And the explanation is actually pretty like well known and expected. It's just because in lower certain temperature, we just don't have an efficient way of releasing the momentum. And I will stop here, and for the summary, if you're interested, please scan the QR code for all the quick application. Thank you so much.
Time for a couple questions.
So a little camera is in cadence, and this is a cadence by stress, and we're mostly focused on 2.29 to 2.49 micron. And that's because of the way that we tower waveforms are really good within that waveform range. So, and then those are also kind of low. So in the future, we would love to take more spec on pulse stack them and try to see if there's a black gamma acquisition signature, for example. Thank you.
Thanks. Hey guys, our next speaker is going to be Neda Hijazi, who's going to be talking about the chemical properties of endworms.
Is this here? Yes.